Hello, we present our paper named Bijective Maximum Likelihood Approach to Domain Adaptation and Semantic Scene Segmentation. The research is conducted in the collaboration between the University of Arkansas, Concordia University, and the University of Wollongong. The typical supervised semantic segmentation learned on the source domain with an input RGB images and the corresponding ground truths. However, it usually performs worse when we direct apply the learned model to the target domain due to the gap between source and target domains. Therefore, to enhance the performance of the model, the unsupervised domain adaptation is applied. The common approaches for the unsupervised domain adaptation is adversarial training, in which this approach utilizes the adversarial loss with weak structural learning. Another approach for this problem is self-supervised training via entropy minimization. In such approach, the adversarial loss and entropy loss with the assumption of pixel independence have been formed to learn the model with weak structural learning. Several other methods take the advantages of privileged information to learn the model. However, this approach requires additional label information such as depth maps. In our approach, we propose a novel method called BiMaL, Bijective Maximum Likelihood Approach. Our approach form is a bijective maximum likelihood loss with global structural learning. In addition, we prove that our approach is a generalized form of entropy minimization and a tractable approach. To summarize, our contributions can be described as follows. We proposed a novel metric, namely, unaligned domain score, to measure the efficiency of the learned model in an unsupervised manner. Further, we extend the proposed metric to a novel loss called bijective maximum likelihood. The loss is computed via bijective mapping function. Theoretically, we prove our proposed loss is a generalized form of the entropy minimization. Thanks to the bijective mapping function, we can sufficiently model the global structure of the segmentation. Our approach achieves state-art results on the unsupervised domain adaptation benchmarks. In our approach, the unaligned domain score metric measures the efficiency of the learned model by the distances between the predicted distribution and the real distribution of the segmentations in the target domain. However, the real distribution of the segmentations is not available since there is no annotation in the target domain. It should be noted that the source and the target domain share the common space of the segmentations. Therefore, we can approximate the target segmentation distribution via the source segmentation distribution by learning a bijective mapping on the source domain. Additionally, we add a regularization term, tau, to further enhance the smoothness of the segmentation results. Now, from the unaligned domain score, we further extended it to be a bijective maximum likelihood loss including two terms. The first terms is the negative log likelihood to learn the global structures via the bijective mapping function, and the second terms is the regularization to learn the local structure. Our bijective maximum likelihood has several important properties. First, there is no pixel-independent assumption in our approach. Second, via the bijective mapping and a regularizer, we modeled both global and local structure of the segmentation. Third, our bijective loss is tractable and invertible, which results in stable learning. Last but not least, our bijective maximum likelihood loss is a generalized form of entropy minimization. In particular, we can prove our loss is an upper bound of entropy minimization. The proposed framework of our approach includes two streams. First, the supervised stream is learned on the source domain by the cross-entropy loss. Second, the unsupervised stream is learned via the bijective maximum likelihood loss on the target domain. Now, we show video demo of our results. Thank you for watching.